Today we are going over an exploration of the FRC kit drivetrain. It's a really common platform for every team who has the option of getting it in the kit apart. So it's used by a large variety of a large amount of teams every season. So it's really common. So even if we don't compete with the kit drivetrain, we have them. We have them running. So we build like an everybot platform, and we also have a lot of partners that have them. We teach people how to use them, and just a lot of the concepts we use in our robot all over the place, not just the drivetrain, can be shown through the kit drivetrain. It's a really common platform. So that's one of the reasons why we're going to start with this as kind of like our exploration. Then we'll dive in to other subsystems and things in future weeks. Okay. So the goals are for you to know like kind of what is the kit drivetrain, what does it do, and then a lot of what the slides are actually is like how does it work. So this is not like the instructions on how to assemble it, that's already provided for you. What we're doing is we're really talking about the concepts behind it and why robots are kind of built the way they are. As much as we can, I'm going to try to keep my language as simple as possible. But if there are words that I use that you're not sure what they mean, please put it in chat and I'll redefine it and try to choose more common words wherever possible. Okay. So this is what the kit drivetrain looks like. The kit drivetrain has been some variant of what's known as the AM14U for a while now. I don't actually know when it started, but for several years. We're on our 4th version, so I think it's been at least 5 or 6 years. Andy Mark is a vendor who sells largely specific FRC products. They do some other robot things related to other areas of robotics, but they got started by engineers who were mentors for FRC teams, Andy Baker and Mark Kors, and they've now expanded out and they have a lot more people working for them, and they produce a lot of awesome products for the FRC community. And one of those is the kit drivetrain. So like I said earlier, it's provided in the kit to all the rookie teams, and then it's also provided as an option for all the veteran teams. So a lot of what we're going to look at is the CAD model. So over here on the left is the virtual model of the kit apart drivetrain. Over here on the right, you have the actual, what it looks like in real life. But a lot of our images, because we're going to like dive into it and kind of piece out individual parts and kind of show exactly what's happening with all of it. Okay, so there are build instructions. There's a full video that they've done that's really good, and there's a full manual. So like I said, we are not going over the build instructions. If you want to know exactly how to build it, go to those 2 links. They do a great job. We're going to talk about how it all, or why it all gets designed the way it does. Okay, so first, what does the drivetrain actually do? So back in our previous video, an overview of the FRC parts, we talked about what drivetrains are. The biggest thing is it allows the robot to move around the field, right? So it allows for a very easy and simple way to build up a drivetrain that is configurable. So there's multiple ways to build it depending on how a team may want to do the game. And then it gives them a platform to put their control system and to put all their other subsystems on so that they can at least compete that part of the challenge. So the robot can drive forward, backwards, turn left and right, and do it very well. So the way it does this is the drivetrain has 2 groups of wheels. There's a left group and a right group. So in this configuration, there are 3 group wheels on the left side and 3 wheels on the right side. We're going to call this up here the front, right? You get to choose whichever one you want to be the front and back, but for this purposes, going towards the right of our screen is going to be the front, and back here is going to be the rear or the back of the robot. So when the groups of wheels all go forward, you can imagine that the robot just goes forward, right? That's really easy. All the wheels on the sides are going forward. So just like your car, all the wheels are going forward. They're all pointed forward. They're going to go forward. If we want to go backwards, we drive all the wheels backwards and we go backwards. That part's easy. Turning is where it gets different from how a car turns. So normally, like a car, you actually steer the wheels. In most FRC robots, we don't do that. Instead, we change the direction and speeds of the 2 groups of wheels. I'm going to try to get that to, there we go. So to turn right, we have to have the left group of wheels going forward, and to turn, and the right group of wheels have to go in reverse, because that kind of allows that whole thing to turn, just like you would move your hands. If you're turning like a steering wheel, your right hand goes backwards and your left hand goes forward, and so the whole robot is able to turn to the right. And the exact opposite happens if we want to turn to the left. And that's the majority of FRC robots drive using that control logic. Basically, it's very easy for our control system to change the speed and direction of our motors. So it's very easy to make this setup work really well. Yep. Okay. One of the main parts of the kit chassis is the frame. So the frame for the AM14U4, is a frame made out of bent aluminum sheet metal. So when they manufacture all of these individual parts, so we can kind of count, there are 6 parts here, right? There are 2 end plates at the front and back. There are 2 inner plates and there are 2 outer plates. And each of these parts start their life as a flat sheet of metal that gets produced, and then there's some machine, there's a variety of different machines, but some machine will go through and cut all of the holes that you see and cut out the outside pattern, and then a different machine will come and bend parts of it, and those bends are what give the part strength. Because if you just have a flat piece of something, just like a piece of paper, it's very easy for that to twist or fold or bend. But if you can actually put a seam into it, so you make like an L, it gets a lot harder to bend that thing. So we get a much stronger frame by having those bends in the frame elements. There are a lot of holes in the kit drivetrain. This is so that you can have various configurations. So a lot of them are used for the assembly. There's places where the wheels mount. There's places where it gets bolted together. And then some of the holes are also set up just for you to attach other things to the frame, right? It's not just the drivetrain. We know we're going to eventually attach stuff for the robot to launch balls or have an elevator that goes up and down, whatever else the robot has to do. So a lot of the holes are designed for that. But then a lot of the holes are also specifically designed for different configurations that you can make the drivetrain into. So we're only going to look at kind of the main, almost default configuration. But if you go back onto the Andy Mark site, there's a whole lot of different options that you can use. And so a lot of those holes are there for that, which is why it looks so weird. And it's like, oh, there's so much to go and it looks kind of complicated. But really, you just find the specific ones that you need and use those, and the other ones are just left over, and that's fine. Okay. The whole chassis is able to either be like long or wide. So if you built it without cutting anything, it would be too big for what's normally allowed in an FRC game. So one of the things we do have to do is cut down the end plates. These come longer than what we were allowed to use to make this configuration. So to cut them, the most basic configuration, or the most basic way to do it, is to use a hacksaw. So it's a saw that you can get at Home Depot, anywhere. They're very common, and they cut through metal very easily. And we would basically clamp it together and mark how long we need it to be and cut through and try to get as straight of a cut as we can so that we can assemble the entire rest of the chassis. So that is one of the things that'll go through in the instructions on how to do it. But that is part of the assembly, is you do have to cut it properly. The way it's all held together, so we have to have fasteners to hold it together. Most of the fasteners you've probably used, if you have not done robots, are just like, you may have had screws in the back of toys or in whatever else you've done, right? You may have put together like IKEA furniture, and there's all sorts of interesting fasteners that they use. The most common one in FRC is bolts and nuts. They'll look a little bit different than some of the screws and nuts you may have used in other things that you built around your house. But they're pretty close to some of what you may see in IKEA. They'll use the little, they'll have hex heads normally, so they'll have a little Allen wrench. I think we'll get to it on the next page here in a second. but the nuts and bolts are what hold all the end rails together so that you can get a nice, strong, full structure. If we held it together with something weaker, everything might be able to like flex and move around, and we wouldn't want that. We want these to all be secure joints that aren't going to move or anything when the robot's driving around the field. Bolts are the part of the fastener that have a head and all of the spiral threads on the outside that get turned into something. Also known as a screw. Eventually you can figure out differences in the two. If you call it a bolt, you call it a screw, people are going to know what you're talking about, and it's okay. Almost all the ones we use in robots have this like hex shape on the inside, so it's not your normal flathead or Phillips screwdriver. These allow us to make the bolts tighter, basically, and they use a Allen wrench or a hex wrench, whatever you want to call it, to turn them into their other fastener. So what we'll use is we'll have a nut on the other side. So the nut is the short one that has spiral threads on the inside. To secure it, use a wrench. So you put the wrench around the outside flats, and that holds it in place while you turn the bolt or screw into it. In FRC and in most robotics applications, we use very special nuts that are called nylon lock nuts. They have this little bit of plastic in here that you can kind of see right here. And that stops the nut from coming back off the fastener. So if we just had a normal nut that you might find in your house somewhere, if we drove the robot around, there's a ton of vibration. The robot's bouncing around, it's running into stuff, and it's very easy for that nut to basically loosen up and then come off. And if that happens enough, you have enough nuts and bolts just no longer secure on your robot's not secure, and your robot starts falling apart on the field. And that's you never want that. You want your robot to stay the way you put it together most of the time. So this is always pointed away from the bolt head. So the bolt kind of screws into the back of this, and the threaded part will stick out from this end up here. Yeah, so basically you just twist those together. You twist them together nice and tight, and they'll stay there throughout the competition, which is what we want. Another type of fastener that gets used is what's called a standoff. So in this, we have the frame like we had before. We've added all the little bolts and nuts into the corners to mount it together. But then we don't have anything kind of securing this inner plate and the outer plate together. So if I were to like squeeze those two, if I didn't have those standoffs, I'd be able to like squeeze them together a little bit. So those standoffs in here, these little pieces of metal tubes, are able to stop me from basically being able to, or stop anything from being able to squeeze those together. It allows just a little bit more structure to it. It makes everything a little bit more stiff. Basically stiff is so it can't bend. And that's what we want. We want a nice stiff frame so it's not bending or twisting in any way. The standoffs in the kit chassis are known as churros. They have this star pattern, so they literally look like churro, the dessert. They're not nearly as tasty. There's no cinnamon involved. And then so a bolt just threads into the hole that's right into the center there and secures. So there's a bolt in both sides of these, securing the standoff between those plates and making the whole structure nice and stiff. Okay, so now that we have kind of the structural elements of the kit chassis put together and why those exist, we're going to start adding the actual movement part. So how do we actually move around the field? The motors and gearbox is the first step. So in the AM1FOR-U, we have two motors. So these black cylinders here are two of our motors. And then this black piece right here is actually a plastic part that comes with it. And it's basically just a cover and a place to mount the motors. Our motors, what they do is they spin when we give electricity to them. So we have our whole control system, which we have a whole nother slide deck on how that works. But when we're able to apply electricity here, we get rotation, which is what we want, and then we use that rotation to move the robot. The gearbox specifically is the first thing, is kind of between the motors and the wheels once we add the wheels. And it helps let us have the robot go at a usable speed. The motors spin very fast, and so the gearbox allow us to drive the robot at a usable speed for what we need it to do, for how heavy the robot is, all of that. Any sort of shafts and axles are spinning parts that you're able to mount other stuff to. There's a variety of lengths and shapes. We'll talk about some specific ones, and we'll talk about what gets mounted to these, but just know if I say shaft or axle, I just mean whatever the kind of long, narrow, rotating thing is, basically. Okay. The kit parts specifically provides a type of motor known as a SIM. It's spelled CIM, pronounced SIM. Like we already said, when electricity is applied to the wires, the output shaft will spin. So we can, none of this part out here spins. This is all stationary. Only this output shaft is what's rotating. So we have mounting holes in the face of it where we can stick 2 bolts, and we can mount this up to the gearbox. And those are on what's called the motor's face. So that's the that's this part right here on the outside. That's called the motor face, and the motor has 2 mounting holes to secure it to the gearbox. Yeah, and then this outer bit, it kind of looks like a Coke can, so it's literally called the motor can. And so it's just the outside of the motor. Okay, so this is kind of what the gearbox looks like in CAD. This was that black part. I changed the color. I apologize for that. But this black this outside plastic part is the same that we had right here. It's just in black in this image. And inside of there, we have gears, which is why this is called the gearbox. It's the thing that holds the gears. Pretty intuitive. So the gearbox uses gears to reduce the speed of the wheels powered by the motors, and to do that effectively so that the motors can still power the robot, but at a speed that's usable, and able to still get the robot to go at the speeds we want, to be able to move things around, be able to push things around. We need to have the gears do that to help us do the reduction in speed. If the wheels were connected directly to the motors, the wheels would spin very fast, but the robot wouldn't be able to drive around, turn, push things, anything like that. So we use the gearbox to allow us to drive at a reasonable speed, but still be able to actually do that with enough force that we can drive around, push things, everything like that. That's what the gearbox does. This specific gearbox is called a Tough Box Mini. In the actual slide deck, you can link to all the pages where you can get a lot more information about them if you want. But for now, we can know kind of what it's called, and I may refer back to that. Okay, so this part is the gearbox housing. So this is what covers the gears. It's a plastic part, and it has basically a bunch of holes to allow for all of the mounting of the gearbox, to mount the motors, and to mount the whole housing to the inside rail of the chassis. So all of that there's a lot of little design elements in here to let the whole gearbox assembly work. Without this plastic piece, everything would just like fall apart. That wouldn't be fun. So there's a lot of little details to make it strong, but also light. So like a lot of these little cutouts are there just to save on material. So they could have been filled in, but then it would have used more material. So they can have like lots of little cutouts to make it a little bit lighter and cost less. Yeah, it all matches up to things that happen on the frame and with the motors. So everything has to be like designed to work together. So you can't just take a random gearbox housing from some other gearbox and slap it on there and hope that it works together. You really have to design them and make sure they're all designed to work in tandem together. Okay, So a brief introduction to how gears work. Gears are tooth wheels, so these things are gears. So they have these little teeth going along the outside. They allow motion to be transferred from one shaft to another. So they'll have like a shaft on the inside that's spinning, that gets attached to the gear, or the gear gets attached to the shaft, however you want to say it. And you can transfer motion. When two gears are interlocked, so when their teeth are set at the right distance apart, so there's a very specific distance they have to be apart so everything can like mesh nicely. They're called meshed. So that's the term we use for gears that are connected together properly. When a small gear turns a larger gear, so we have this small gear up here and it's turning a larger gear, the larger gear will turn slower than the smaller gear. So if the small gear up here only spins, or the small gear spins one revolution, this slower gear is going to spin less than one revolution, right? So we don't need to go into exactly how or anything we need, or like what the ratio is or anything. We don't need that yet. But all we need to know is that the smaller gear is going to be spinning faster than the bigger gear. And that's why we get, this is called a gear stage, and the specific type of gear stage is called a reduction, because this is going faster and we reduce the speed of this shaft. Our specific gearbox needs to have even more reduction than what a single gear stage can do for us. So then we'll get into multiple gear stages. So when we need to reduce the speed even more, we can basically connect multiple gear stages together. So the way the Toughbox Mini does it is we have a first stage, which is up here in blue. So these gears right here are attached to the motor output shaft. So we're looking kind of like directly at the gearbox, looking at it from the front. So we have the motor face back here. We have the motor housing all the way around it. And we have these gear here that's directly attached to one motor output shaft. And we have this other gear here that's attached to another, to the other motor output shaft. And both of these gears are meshed to this big blue gear that is behind these pink gears, right? So there's some depth. You can see it right here. So you have this gear in the back, and these two gears are in front of the gear stage back there. So our second stage is this pink set of gears. And when we do that, when we have these multiple gear stages, we'll end up with 3 different speeds, right? So we'll have the green gears spinning the fastest. These are the ones directly from the motor, so they're spinning the fastest. Then we have that gear reduction in the first stage to this yellow gear, the big yellow gear. And since this big yellow gear and the small yellow gear are both on the same shaft, that means they have to be spinning at the same speed, right? The shaft can't have different speeds happening directly on it if they're both coupled to it, if they're both attached to it. So then they're going at the same speed. And then we get one more gear reduction because we have this smaller gear here connected, meshed with this bigger gear on the outside. So this red gear is going the slowest. So we get fastest, medium, slowest when we have this two stages of reduction in our gearbox. Okay. Real quick, one of the parts of the assembly process is how you actually mount this gear to the motor output shaft. So this is what it looks like put together, and this is what it looks like as like a breakaway or a exploded view. So we have all of the parts coming off of it, and these would slide on. So this is the same output shaft that we discussed earlier. These little bronze pieces right here, orange, whatever color you want to call them, are spacers. So they stop the gear from basically touching the motor face that isn't spinning, right? So this output shaft is spinning. If the gear was like up against this, you'd have this not spinning and the gear trying to spin, and that wouldn't work very well. You very rarely want non-spinning thing touching spinning things unless you're like intending for it to happen. So the spacers prevent that. This little green, the arrow from the green, this little part right here is called the key. The key sits in this slot that's in the output shaft, and that lets the gear that also has a slot in it make sure that it actually rotates with the shaft. If the gear just had a circular cutout, if the shaft was just a pure circle, if I grabbed the gear and held it, the shaft on the inside could just spin because there was nothing connecting the two, right? Like, yeah, they were on top of each other, but the shaft on the inside could just spin around, just like a fidget spinner would, and you wouldn't actually be able to get any of that rotation to the wheels or anything if I was stopping it from spinning. So because we have this key in there, we physically connect this gear to the output shaft. So then when the output shaft spins, the gear has to spin unless we somehow destroy the key or something else happens to it to where it breaks. But as long as it's there and kind of connecting the two of those things, you can't stop the gear from spinning because it runs into the key, basically. The gear that is mounted to the output shaft of the motor is known as a pinion gear. It's just a special word for it. It just means the one that's basically on the motor output shaft. And the last little thing that goes on is this little clip. This is circular. It has little teeth in it. Let's probably get a better view on this slide deck. But it's called the retaining ring. And basically when you push it on, it takes a little bit of force to push on, and it makes it very hard to pull off. So then the gear can't just come flying off the end, and it's going to stay where we locate it on the output shaft. Okay, so here's a better view of how the key works. The key fits into this slot here, and there is a slot in the gear that you can see too. The gear is just shown as transparent, so you can see the inside of it. And like we already said, if the key wasn't there, this gear could spin around it even if the motor wasn't spinning, or if the motor was spinning and you stopped the gear, it wouldn't necessarily want to connect. But once the key's in there, these two, the gear and the output shaft, have to be spinning at the same speed. The other way we accomplish basically a very similar thing, except without having to have that extra part, is by having our shafts not be circular, but instead be hexagon profiles. So this is known as a hex shaft, and this gear has a hex opening. So there's the 6 sides here, there's 6 sides here. So when you put them together, now even without that key, I can't just spin the gear on the hex shaft. Those two things have to be spinning together at the same speed. And that's the important part, right? They're meshed together, and they're going to always be spinning at that same speed. So that's the hex gears do that with hex shafts, and so do keyed shafts with a key and a gear that has a key slot as well. Okay, so this is what happens when we want a shaft and something to spin at the same speed. When we don't want them to spin at the same speed, so if we have a stationary thing, so say the gearbox housing, right? The gearbox housing isn't rotating at all. It's going to be stationary and mounted to the frame, but it's going to have shafts inside of it that are spinning. So when we have that difference in speed, we use bearings to account for that. So the bearings allow a shaft to spin very smoothly and be mounted to something that isn't spinning. Their number one job is to reduce friction. So they allow for very easy spins. They're the same type of bearings that are in a skateboard or in a fidget spinner or anything like that. The same concept of bearings work the same way. So instead of just having a shaft like spinning and rubbing inside of a piece of plastic or another piece of metal, you have a special part that has 2 rings of metal, and it has ball bearings on the inside. So these little balls, these little spherical bits of metal are able to roll around on the inside, so that when you have a shaft inside here in this green part, which is known as the inner race, you have a shaft here. And so as it spins the shaft, the green part will spin with it because the green part can spin very freely. The blue ball bearings will roll around the outside, and this red outer race will stay in place. So this won't rotate at all. This will be attached to the gearbox housing or the frame plates or anything else that we need on the robot. And this inner race, this green part, will be the bit that's spinning around and allows the shaft to spin nice and free inside with very little friction. In a lot of our robot applications, one of the things that gets a little confusing for people is not all the bearings are the same. So this is kind of just a generic bearing. Our bearings have a little bit more to them. A lot of times in the CAD model, you won't see the ball bearings because our bearings have covers over them, so don't get dirt or grime on the inside, so we can keep them clean. And then some of our bearings will also have this orange part here that's known as the flange. So the bearing flange is just this raised lip, and it allows us to very easily place a bearing into a flat part that just has a hole in it. So if we didn't have this flange and we tried to put a bearing through a hole, it would just slip right through the hole if we could push on it from either side. Where when you have the flange, is if we push on it from this side, it can't go through this metal sheet. So it's very important to think about which side of the plate you're inserting it from. So if we expect that maybe it'll be pushed on from this side, we want to make sure the flange is here, so that if it is, it can't go anywhere. If in that same application we had this on the other side and we pushed on it from the same direction, it would just pop right out, and that would be a big problem. For specifically the KitBot robot, the flanges are all pushed in from the inside of the robot, and that's really important. There's one of the really common mistakes is to have one of these be the wrong way, and literally your entire drivetrain, the part that actually moves around, can just fall apart while you're driving if you don't get the flanges in the correct order or in the correct direction. These are what the actual bearings look like. So these are images of what our real bearings look like. There are a variety of different types of bearings. They can have different outside sizes, which are called their outer diameter, or abbreviated to OD. Bearings can have different inside sizes, which is called their inner diameter, or abbreviated to ID. And then you also have different shapes for the openings, like we just saw with our different shafts, right? We have round or hex. And then most of the FRC bearings, the ones we'll use on our robots, have this goldish ring on the inside, which is called the shield. So this bearing right here is a 3-inch ID round bearing. So the inside of this bearing has a 3/8 of an inch round opening here. A lot of times we'll just spec the bearings kind of initially by their inner diameter, and then you have to also look up their outer diameter because they can be different sometimes depending on what you're doing, to make sure you have the right outer diameter too. This example is a 3/8 inch ID round bearing with flange. So this bearing is just a round bearing without a flange. This bearing has that little lip on the back, so that's what's called the flange. And then the last example is a 1/2 inch hex ID bearing. So you can kind of see here that there's a little bit of a flat. You can kind of see the corners in places. So this has 6 sides on the inside. So it fits a 1/2 inch hex shaft. And then it also has a flange as well. One of the things that gets a little interesting sometimes is how the ends of the shaft work. So you may want to have most of the shaft be a hex shaft so that you can have a gear easily attached to it without having to have the key or anything like that. So you want to have the hex that way. but then on the ends, we can change them to be like a round shaft. So then we can use the very common round bearings, because it's a lot cheaper and a lot easier to use round bearings than it is to use hex bearings. But you use the advantage of having the hex gears if you have a whole entire round shaft. So the kit drivetrain uses a couple of these small shafts that have hex for the middle part, and they have round on the ends just where they sit inside the bearings. The other advantage of this is that since this is a 3/8 hex on the inside and a 3/8 round on the outside, you can't actually slip the shaft either direction. So if these bearings are both held in place, if I try to like move this shaft, if I try to move this shaft, the little bits of the hex won't fit through the round opening. So that lets you basically like hold the shaft in place without having to add any other parts, any other additional pieces to the robot. So you get a little bit of an advantage there as well. Okay. Another part of the kitbot that gets used is this clip that's in blue here. It's actually black in real life, but it's easier to see when I make it blue. It's called an Eclip. It's not really the shape of an E, but it's kind of close. Some of the other versions are closer to an E. They have a little tab here that makes them look a little bit more like an E. For the kitbot itself, we have this shaft down here. This is kind of the back of the gearbox. It's a little hard to tell exactly where that is. So it's this same shaft here. There we go. Okay. And then it's this shaft right here coming out of the gearbox, and we're just kind of looking at it from the back now. So if like this housing wasn't here, that's kind of the view we're about to look at. So this E-clip holds the gear from being able to come too far back. So if you were to not have this E-clip, this gear right here could pushed back too far, so it could come back and like hit this other gear on top, which would be bad. This shaft could also be pulled straight out the front, because right now this E-clip hits the gear, so it doesn't let the whole shaft like slide out. If you didn't have the E-clip, the whole shaft could slide out. That'd be very bad if you were just driving around the field and all of a sudden this shaft was 2 inches that way and now no longer attached to this gear. Your robot just wouldn't drive anymore. It basically just gets pushed right into a little groove that's made into the shaft. So this shaft gets a little bit more complicated, right? We have this hex on the outside here. This is a 1/2 inch hex. The gear has a 1/2 inch hex too. There's a little groove specifically cut to the right size so this E-clip can go into it. And then they also change this shaft end for a bearing. So the bearing can go spinning right around this end of the shaft. There's a little bit more shaft here in this model for a sensor to be put on it so we can know how far the robot's driven or how fast the robot's driven as well. So there's a lot of different things. You don't have to have the shafts all the same size. You can change them a little bit in different ways to meet the purpose you're trying to. So in this case, we need to be able to hold this gear in place and hold the shaft in place, and the E-clip does that very nicely with a very small and inexpensive part. Okay, so now that we've covered the gearbox is a big part of it. There's a lot of little details in there, so we're going to be stepping out and getting to more of the larger parts of the robot and how it drives around. The output shaft, so this is that same shaft that has the E-clip on it. This is just the other side of it now, so we're looking at the other side of this shaft. Is the output shaft of the entire gearbox. So each motor has their own output shaft, but then the gearbox also has an output shaft. And so it's a 1/2 inch hex shaft here, and this output has hex bearings as well, so that they're able to spin freely. And they have those ball bearings on the inside like we talked about. So this shaft is able to spin very quickly, and it's not rubbing against anything on the frame, and it has very little friction, which is what we want. Okay, let's look at the wheels that are used on the kit drivetrain. So they use what's called an Andy Mark high grip wheel. It's a wheel specifically designed for FRC robots. It's a molded plastic wheel, so all of this material in black in here is a very strong plastic, and then it has a rubber on the outside, so it has a lot of grip on the carpet so that it can't be like it's not easy to push it sideways, and when you're actually driving, you don't like have the wheels spinning and the robot not driving around. That would be bad. Each wheel has a circular hole pattern. It's not the easiest to see in this. It'll be easier in the next CAD, but there's basically 6 holes all the way around this that allow you to mount different things to the wheel. And the kit drivetrain has 6 wheels, 3 on each side. Two of them, or 1 on each side, is a center wheel, and then there are 2 corner wheel assemblies on each side as well. So the way the center wheel works is it's attached directly to this output shaft. So it spins at the same speed as the output shaft. And it does that by the way this whole assembly works. This wheel is also how we're able to transfer the rotation of the gearbox to the outer wheels too. This whole assembly has these pulleys on the outside. We'll talk about especially about what those are in just a second, and those would help power the outer wheels. And so there's a bunch of little items bolted to it, and we're going to go through them one at a time. So the first item we're going to look at is the Hex Hub. A hub is a part that allows a wheel or a mechanism to mount to a shaft. So sometimes you'll have the feature directly built in, like we did with the gears, right? So several of our gears had a hex shape directly cut into the gear itself, like this. Other times you'll have a part like a wheel that may just have a circular opening, and they're designed to be used with a hub. So then you can bolt this hub to the wheel, and now you have this same metal hex opening here. And so that part can be a lot stronger because it can be metal, and then you can still use a plastic wheel for the rest of it. So this hex hub here is used in the center wheel assembly to connect the wheel to the output shaft of the gearbox. In addition to the hex hub, we also have pulleys on the center wheel module. So these 2 pulleys are what allow us to connect the center wheels to the corner wheel assemblies. This is more of a specific thing for if you're actually building it, but it's a useful thing to know because the instructions don't always cover it, and it's just handy for robots in general. Whenever we're tightening bolts, what we normally want to do anytime we have like a whole set of bolts in some sort of pattern is we'll get all 6 loosely connected. So we'll thread them in a couple threads. We'll get them kind of loose in there, but not tight yet. And then as we're tightening, you want to use some sort of like alternating pattern. You don't want to just go and tighten fully in like a circle, because what will end up happening is you'll tighten one side a little too tight, and then it'll shift and it won't quite be right for the other side. So we normally try to use a star pattern type thing where if I start at this red bolt to tighten it in, then I would skip over to this orange one. I would then skip over to the yellow one. I could skip back to the green one, back to the blue one, back to the purple one. And now I've basically done it a lot more even than if I would just go red, green, orange, blue, yellow, purple. And so that happens quite a lot on a bunch of different parts of our robot. In general, you always want to try to tighten things evenly around anything that's going to be circular, or anytime you're going around like a big plate. The more evenly you can tighten up the bolts, the better, because things will like kind of stretch and move a little bit as you're doing the tightening. So if you can do it evenly, it helps. Okay, so what do pulleys and belts do? So the pulleys on the kit apart drivetrain are similar to gears, right? They're both toothed wheels, so they have these little teeth in here too. But they're not interchangeable. You can't use a gear and a pulley together. That's not how it works. You have to use specific gears together, and you have to use specific pulleys together. But a pulley don't connect directly to each other like the gears do. They need a belt, or in this case, what's called a timing belt. And the belt has teeth on itself, so they have the like kind of the opposite teeth on the belt, and they'll mesh the same way kind of a gear teeth will, and they'll grab onto multiple of these teeth and they'll kind of sit inside of here, and then you're able to have, as one of these pulleys rotates, the other one will rotate at the same speed since they're the same size pulley. And you can basically just transfer power or transfer rotation over a longer distance. So as instead of with gears, like if we wanted to have a shaft in this pulley and a shaft in this pulley driving each other, and we were doing this with gears, we need a lot of gears because they'd all have to connect to each other. But with pulleys and belts, we can have a long belt and only have 2 pulleys. So we get a lot longer distance that we can transfer the rotation over. And they get that they still spin together. So when the gearbox is spinning, the center wheel can rotate and the corner wheels can rotate too because they're connected by this belt. The corner wheels are a little bit different than our center wheels. Because instead of being spun by a hex hub and driven by that hex shaft from the gearbox, the corner wheels are connected by the belt to the center wheel. So that means this pulley is already spinning. So we don't actually need the shaft itself to spin since the pulley is doing the rotation for us. And so the kit apart chassis takes advantage of this by putting the bearings, instead of having the bearings in the plates like the center one does, where it has those hex bearings on that hex shaft and that's where it's spinning, you actually have the bearings here mounted in the pulley and in the wheel, so the shaft itself doesn't have to rotate, and only the wheel itself and the pulley will do the rotating. So you can see there's a bearing here. It's a little hard to see. I probably should have colored these. And a bearing here. And so now this inner shaft, which is actually just a bolt we'll look at in just a second, doesn't have to rotate at all. And so that simplifies the entire process by having this non-rotating shaft and just having the wheel and the pulley rotate around it. So the corner wheel assemblies are mounted with an axle bolt. So this is what it looks like in real life. It's colored in red in our CAD model, so you can see exactly what it does. And these bolts don't spin. You do have a nut on the back side of this, so we'll put a nut on the threads at the back here. It'll be like kind of on the inside of the robot, so we can't see it in this picture. And that'll stop it from coming out, so we wouldn't be able to pull the bolt out of the robot. So you have the nut on the back side. And you don't really want to tighten these too tight. You don't want the you don't want to like squeeze the plates together with this bolt and nut at all. You just want it there so that it can't come off. But these bolts aren't really there to help stiffen the frame at all. They're just there to help mount the wheels in place. And so the bearings, the inner race of the bearing in this case works a little bit different than what we talked before. The inner race will be on this bolt. Let me see if I can get back to bearings. The inner race will be on the bolt here. The outer race will be the part that's actually doing the rotating because it'll be in the pulley or in the wheel. So it'll be spinning with the pulley and spinning with the reel. And the inner race will be stationary, mounted to the bolt. Okay. Another part of this assembly are more spacers. So we briefly talked about spacers on the motor output shaft. We had a couple spacers. These assemblies need spacers as well to stop the wheel from being able to shift side to side. We want to make sure that everything is located exactly where we want it. If it starts moving, maybe the belt would be moving, the belt might come off. We don't want any of that. So we have spacers on this side. This is a spacer that's in the center wheel assembly. On the corner wheel assemblies, they have this small orange spacer here, and they have a bigger one on the back side. And those just let us place the wheels exactly where we want them along the shaft. And then once those, like the plates are on the outside, it's bolted together, you can't move the wheel at all, which is what the spacers do. They just take up room on the shaft to stop anything from sliding along it. Yeah, we don't want anything sliding side to side. So if you didn't have the spacers, the wheel would be able to shift back and forth. Okay. I actually did pretty well on time. So, so things to remember. This type of drivetrain and the majority of FRC drivetrains turn by changing the direction and speeds of the wheel on each side of the robot. The gearbox is what converts the motor's fast speed to a usable speed for the wheels. Gears and pulleys are used to transfer rotation from the motors to the wheels. Bearings allow shafts to spin smoothly. They reduce friction. A hub is a part that allows the wheel or mechanism or anything else we want to mount to a shaft to spin at the same speed as the shaft. And then spacers and eclips are used, and retaining rings are also used in this video too, are used to hold items in position along the shaft. Yeah, so we had a question about how the gearbox changes speed. So I'll get back to the gearbox real fast. So we do have the gearbox, the robot is able to change speeds. So we're able to tell the motors roughly how fast to spin. But what we want to do with the gearbox is limit the max speed of the robot, because otherwise we're not using all of the energy effectively. So by having the gearbox, even though we can tell the motor to go full speed, the robot isn't going as fast as that would be without the gearbox. It would go way too fast. So we want to be able to use the whole range of the motor speed. So we're very energy efficient. And so yes, we can control the speed with the control system. So we can tell it to go a little slower. We can tell it to go faster. But if we didn't have a gearbox, you wouldn't be able to use it all. You can, if we wanted the robot to go faster than what the max speed is with the gearbox, you could change what gearbox you were using. So you could change the different sizes of gear. So all of these sizes are specifically set to let it go a certain max speed, basically. But there are different gears you could get to change that. And we'll go into more about how the gearboxes are actually designed later and how we kind of choose those speeds and how we set the speeds for robots in a future presentation. Okay, so I think that about wraps up this presentation. Thank you all.